Vector Calculus, Lecture 16. And we are studying functions of several variables, in particular, the directional derivative, gradient, and what we'll discuss today are tangent planes to surfaces. So let's recall we have a function of two variables, say z equal f of x, y. And if we want to get some picture of what this function looks like, we can try to sketch the graph. The graph is a surface in three-dimensional space. So over some region of the plane where the function is defined, you have this surface. And over the point xy in the plane, if the value of the function is z, you take the point with coordinates xy, f of xy. So this surface is the graph of the function. Or we can look at level curves. So the level curve is the set of all points xy in the plane, R2 is the plane, where f of xy takes on a fixed value z naught. So this is the level curve, f of xy equals z naught. And you will have various curves for different values of z naught. Now, the analog of a derivative in a calculus, in calculus for one variable, the derivative tells you something about the rate of change of the function as x varies. But if you're in the xy plane and you take a point, x naught, y naught, you can ask, how does the function change as you go? Well, there's more than one direction you can go in. Let's see, just 1 second. Yeah. You can go in the x direction, you can go in the y direction, or you can go in any direction for any vector u. So we can say if we fix a non-zero vector u, let's say we're looking at functions in two variables with coordinates u1, u2, and length 1, the directional derivative of the function f in the direction u at the point AB is the following. So in the plane, here's the point AB. Let's say this is the vector u. You look at the line through the point AB parallel to u. So a point on this line will have coordinates a plus u1h, b plus u2h. And you look at the difference in values of the function between these 2 points, f of a plus u1h, b plus u2h, minus f of b. And you divide by the length of this vector. This a plus u1h, b plus u2h is the same as ab plus h times the vector u1, u2. Or ab plus h times the vector u. This vector has length 1, so the length of this is h. So if you divide by the length, the length of this vector, that's h, and you take the limit as h goes to 0, and that's the directional derivative of the function f in the direction of u. And we can express this in a very nice way. So let me draw this picture again. So here's the vector u with coordinates u1, u2. And here's your vector AB, and you take the line through AB parallel to u. So a point on this line has coordinates. Let me use the same variable as the book does in this case, S. This is A plus SU1, B plus SU2. So if I take and I can so I can look at F at this point, this is F of A plus SU1, B plus SU2. This is really some function of S. So G of S is the value of the function F, right? We're looking at a function Z equals F of XY. We're looking at the value of the function F at this point, which depends on S. So G of S is the value of the function F at this point. And so G of A plus SU1, B plus SU2, F at that point, minus F of AB, this is the same as G of S minus G of 0. And if we divide by S and take the limit as S goes to 0, this is the derivative of G at 0. But of course, this is exactly the directional derivative of F at the point AB. So again, I'm just reviewing the definition of the directional derivative. The directional derivative of F at a point AB, you go F plus SU1, BU, S plus SU2. That's the value of the function here, minus the value of the function here, divided by the length of this vector, which is S. But that's G of S minus G of 0, that's G prime of 0. But by the chain rule, G prime of S for any point S, that's dg ds, is dg dx dx ds plus dg dy dy ds. This is x of s. This is the y coordinate, y of x. So this is I'm sorry. This is df partial of f with respect to df ds is the partial of f with respect to x, dx ds, plus the partial of f with respect to y, dy ds. That's the partial of f with respect to x at the point AB, and dx ds is u1, plus the partial derivative of f with respect to y at AB, dy ds is u2. This is the same as if we took the vector fx at AB, comma, fy at AB, and took the dot product with the vector u1, u2. And this is exactly what is called the gradient of f at AB, dot product with u. So we worked out the formula that says the directional derivative of f in the direction of AB is the gradient of f dot product with a unit vector in the direction in which you are taking the derivative. Let me just look at maybe a couple of problems. So this is in this section 15.5, exercise 21. We have the function f of xy equals x squared minus y squared. The point with coordinates 1, 3, and a unit vector u with coordinates 3/5 minus 4/5. So the partial of f with respect to x at any point xy is 2x, or f sub x. And f sub y, which is the partial derivative of f with respect to y at any point xy, if you differentiate this with respect to y, you get minus 2y. So the partial derivative evaluated at 1, 3 is 2 times 1, or 2. The partial derivative with respect to y at 1, 3 is minus 2 times 3, or minus 6. So the gradient of f at the point 1, 3 has coordinates 2, minus 6. And our unit vector is this. So the directional derivative of f in the direction of u at the point 1, 3 is the gradient of f at 1, 3 dot product with u. The gradient of f is 2 minus 6, and u is 3/5 minus 4/5. And this dot product then is 6/5 minus times minus is plus, 24/5 is 30 over 5, or 6. So that's the answer. Let me do another exercise. Let's say number 31. So in this problem, we have the function f of xy is x squared minus y squared minus 9. We're looking at the point in the plane 1 minus 2. Find unit vectors. So this is the problem. Find unit vectors that give the direction of steepest ascent and steepest descent at P. So this we're called the directional derivative of u of a function f at any point AB is the gradient of f at AB dot product with this unit vector u, which is the magnitude of the gradient vector times the magnitude of u times the cosine of the angle between them. U gradient of f at AB, and here's this angle theta between them. But we take a unit vector for the direction, so this is 1. So, and this is constant. The only thing that varies with u is the angle theta. cosine goes from -1 to +1. So you have steepest ascent when cosine theta is its maximum value 1, which means theta is 0, which means u is parallel to, or in the direction of, the gradient of f at AB. So here we have a function x squared minus y squared minus 9. The gradient of f at any point x, y, the partial derivative of this with respect to x is 2x. The partial derivative with respect to y is minus y. So the gradient of f at the point 1 minus 2 is 2, 4. So steepest ascent is when you are when you have a unit vector in the direction of 2, 4, the length of the vector 2, 4 is the square root of 2 squared plus 4 squared, which is the square root of 20, or 2 root 5. So if I take u to be 1 over 2 root 5 times the vector 2, 4, which is 1 over root 5 4 over 2 root 5, or 1 over root 5, 2 over root 5. This is the direction of steepest ascent. When is the directional derivative as small as possible? When cosine theta is as small as possible. That's -1, which occurs when theta equals pi. When theta equals pi, you have the gradient going in one direction, and u, the unit vector, going in the opposite direction. So in this case, for steepest descent, we'll have the vector minus u, minus 1 over root 5, 2 over root 5. So this is the direction of steepest descent. And when is there, in what direction is there no change? That's when the derivative is 0. Cosine theta equals 0, theta is pi over 2. So u is orthogonal to, or perpendicular to, the gradient of f at AB. So the gradient of f is 2, 4. So something perpendicular to 2, 4 will have coordinates -4, 2 divided by the length. We want a unit vector, 1 over the square root of 20. So this is -2 over root 5, 1 over root 5. So this unit vector is a perpendicular or orthogonal to this unit vector, as you can see by taking the dot product. Now, everything carries over in exactly the same way when we are looking at functions of 3 variables. So functions of 3 variables. We have w as some function of x, y, and z. And in this case, the gradient of f at x, y, z is the vector whose coordinates are the 3 partial derivatives of f. Partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. And if you want to compute the directional derivative of f in the direction of a unit vector u in 3 dimensions at the point, let's say ABC, that's the gradient of f at ABC dot product with u. So this is exercise 59. We have the function f of x, y, z equals x squared plus 2y squared plus 4z squared. So this is a function in 3-dimensional space. We take a point with coordinates 1, 0, 4, and we want to find the directional derivative in the direction of the vector whose coordinates are 1 over root 2, 0, 1 over root 2. So these are the 3 coordinates of the vector, and you can check that the length of this vector is 1. So what is the gradient of f at a point x, y, z? Differentiate with respect to x, you get 2x. Differentiate with respect to y, you get 4y. Differentiate with respect to z, you get 8z. So the gradient of f at the point 1, 0, 4, when x is 1, this is 2. When y is 0, this is 0. When z is 4, this is 32. What is a unit vector in the direction of greatest increase, maximum increase? That's the direction of the gradient. So we take u to be 1 over the length of this gradient vector times the vector. What is the length of this vector? The coordinates are 2, 0, and 32. 2 squared plus 30 plus 0 squared plus 32 squared. That's square root of that. Times this vector, 2, 0, 32. Let's see, the length of this vector, 32 squared, is 2 to the 10th. That's 1024 plus 4 is 1028. So that's 1 over the square root of 1028 times the vector 2, 0, 32. Let's see, 1028 is 2 squared plus 32 squared, which is 2 squared times 1 plus 16 squared, just factoring out 2 squared. So this is, so the square root of 1028 is 2 times the square root of 16 squared is 256 plus 1 is 257. So this unit vector is 1 over the square root of 257. Oops. And 2 into this is 2 times 1, 0, 16. So I can just write 1 over 257 times 1, 0, 16. Or if you like to write things in terms of I, j, and k, this is 1 over the square root of 257, I plus 16k. So that's a unit vector in the direction of maximum increase. And what is the rate of change in that direction? It's the derivative, the directional derivative of u of the function f at the point 104. That's the gradient of f at 104 dot product with u. The gradient of f is 2032, and the vector u is 1016 over the square root of 257. So this is 2 times 1 plus 0 plus 16 times 32 over square root of 257. This is 2 times 1 plus 16 squared. So this is 2 times 257 over the square root of 257. So this is equal to 2 times the square root of 257. And the directional derivative, if we take the vector, so this u is the direction of maximum increase. This is a different u. This is a unit vector. We take the directional derivative. Maybe I should have called this, I don't know, u max. If we take the directional derivative of the function in the direction of this vector u at the point 104, that's equal to the gradient of f at that point. The gradient of f, again, is 2032 dot product with 1 over root 2, 0, 1 over root 2. We get root 2, 0, 16 root 2. Sorry. Root 2 plus 0 plus 16 root 2, we get 17 root 2. We get a scalar. Okay. So this is just, these are basic calculations with the gradient to calculate directional derivatives and also directions of maximal increase, greatest increase and greatest decrease in the value of a function. Now, let's go back to looking at a function of three variables. If you have a w is some function, all right, it's capital F of x, y, z. So the graph is in four-dimensional space. And this is impossible to draw or visualize for most everyone, as far as I know. Impossible to draw or visualize. But we can consider the analog of a level curve for a function of two variables, which is a level surface. So it's all points f of x, y, z equal to some value. So if you look at just the simple level surface, f of x, y, z equals 0. So this is all points in x, y, z space, whatever it might be. All points where the function takes on the value 0. So this is some surface in three-dimensional space. Now, suppose this is part of the surface, and on the surface you have the point x, y, z. So f of x, y, z is equal to 0. Or maybe just to keep this in sync with the let's call this point ABC. So we have a point in three-dimensional space where f of ABC equals 0. Suppose we let r of t be a curve lying in the surface f of x, y, z equals 0. So in this surface, we have some curve, r of t. So let's say r of t, this is a vector value function. It has coordinates of x of t, y of t, z of t. And so because this curve lies in the surface, f of r of t, which is f of x of t, y of t, z of t, that's identically equal to 0 for all t. What is df dt? So by the chain rule, df dt, so f is a function of three variables, and each variable is a function of x. So the composite function is a function of just of t, right? Each of the coordinates is a function of t. So df dt by the chain rule is the partial of f with respect to x, dx dt plus the partial of f with respect to y, dy dt plus the partial of f with respect to z, dz dt. This is the dot product of the vector partial f with respect to x, partial of f with respect to y, partial of f with respect to z, dot product with dx dt, dy dt, dz dt. This first term is by definition the gradient of f. at the point x, y, z. And this is by definition the derivative of r prime of t. What f of r of t is 0. It's just identically 0. So df dt is going to be 0. So what this says is that the gradient of f at x, y, z, if the dot product with a vector is 0, it means the two vectors are perpendicular or orthogonal. So the gradient of f at x, y, z is orthogonal to the curve r of t, to the tangent vector r prime of t, for every curve r of t lying in the surface. So here we have the following picture. We have the surface f of x, y, z equals 0, the level surface. Take a point A, B, C on that level surface. Let r of t, or let C, be any curve on the surface passing through the point A, B, C. So on this level surface, you have a curve C. And so let's say C is parametrized by some function r of t with coordinates x of t, y of t, z of t. So the tangent vector r prime of t at the point ABC, that tangent vector is perpendicular to or orthogonal to the gradient of the function f at this point ABC. So at this point, we have the gradient of f at ABC, and every curve going through the point ABC is perpendicular to this gradient. So every curve C has a tangent vector r prime of t orthogonal to the gradient of f at this point. So every tangent vector lies in the plane. What is the plane? It's the plane through the point ABC orthogonal to the gradient. So we learned, forgot, and have to relearn, what is the equation of a plane passing through a point and perpendicular to a given vector? It's given by, take the coordinates of this gradient has coordinates, partial derivative at ABC with respect to x, with respect to y, and with respect to z. So it's going to be that the partial of f with respect to x at ABC times x minus a plus the partial of f with respect to y at ABC times y minus b plus the partial of f with respect to y at ABC times z minus z equals 0. This is a plane. This is the plane orthogonal to or with normal vector gradient of f and passing through the point ABC. And the tangent vector to every curve going through this point lies in this plane. So every curve going through this point, no matter what curve it is, at this point is perpendicular to this gradient and lies in this plane. And so this plane is called the tangent plane. So the tangent plane to the level surface of a function, or to the points in space where f of x, y, z equals 0, it's the plane through that point with normal vector equal to the gradient. So let's do an example where compute a tangent plane. So suppose we have the ellipsoid f of x, y, z equals x squared over 9 plus y squared over 25 plus z squared equal 1 or minus 1 equals 0. So this is our function. So the gradient of f at any point x, y, z, differentiate with respect to x, you get 2 over 9x. Differentiate with respect to y, you get 2 over 25y. Differentiate with respect to z, you get 2z. That's the gradient. And suppose you take the point x, y, z equal to 0, 4, 3/5. So f at 0, 4, 3/5 is 0 squared over 9 plus 4 squared over 25 plus 3/5 squared minus 1. This is 16 plus 9 over 25 is 1 minus 1 is 0. So this is the point ABC lying on the surface. And so what is the tangent plane? So the gradient of f at 0, 4, 3/5 is 0, 8 over 25, 6 over 5. X is 0, y is 4, z is 3/5. So the tangent plane to this ellipsoid has the equation 0 times x minus 0 plus 8 over 25 y minus 4 plus 6 over 5 z minus 3/5 equals 0. And you can simplify that a little bit if you like, but that's what it is. Now, if we come back to functions of two variables, we have a function z equals f of x, y. this is the same as f of xy, z minus f of xy equals 0. So if we define the function capital F at x, y, z to be z minus f of x, y, so for the function z equal f of x, y, you might have the surface, the graph, z equals f of x, y. So if you take some point in the plane AB, on the surface, you have the point with coordinates AB, f of AB. And if we want to find the tangent plane at this point on the graph of this function, that's exactly like looking at the function capital, function of 3 variables, z minus f of xy, and wanting to know what is the tangent point at a point on this level surface where z equals f of xy. So we want to find the tangent plane at the point AB, f of AB. AB, f of AB solves this equation. It's this point on the surface. We want to find that tangent plane. So if capital F of x, y, z is z minus f of x, y, what is the gradient of capital F at x, y, z? The partial with respect to x is minus f sub x at x, y. The partial with respect to y is minus f sub y at x, y. And the partial with respect to z is 1. So the gradient of f at the point AB, f of AB, is going to be minus f sub x at AB, minus f sub y at AB, 1. And the equation of the tangent plane is gradient of f at AB, f of AB. Well, it's minus the partial of f with respect to x at AB times x minus a, minus the partial of f with respect to y at AB times y minus b, plus 1 times z minus f of AB equals 0. If we rewrite that, we get, keep z over here and bring everything to the other side. Z is partial of f with respect to x at AB times x minus a, plus partial of f with respect to y at AB times y minus b, plus f of AB. So this somewhat lengthy formula is the equation of the tangent plane to a surface in 3-dimensional space, the graph of a function of 2 variables. So for any point AB, this is the equation of the tangent plane to the surface at the point AB. So for example, we take the function f of x, y equal to 32 minus 3x squared minus 4y squared. We see that f evaluated at the point 2, 1 is equal to 32 minus 3 times 4 minus 4 times 1. That's 32 minus 12 minus 4 is 16. So the 0.2116 lies on the surface, the graph of this function. So the tangent plane, right, so this is f sub f, this is f. What is the partial of f with respect to x? It's minus 6x. The partial of f with respect to y is minus 8y. So when x and y are 2 and 1 respectively, fx at 2 and 1 is minus 12. Partial of f with respect to y at 2 and 1 is minus 8. So plugging into this formula, the tangent plane has the equation minus 12 x minus 2 minus 12 makes this plus 12 minus 8 makes this plus 8 y minus 1 plus f at AB, which is equal to plus 16. So this is 12x plus 18y minus 12 minus 8 minus 20 plus 6. No, is that right? Oh, sorry, these are pluses. This is partial of f with respect to x at AB is minus 12 minus 8. So this is minus 12x minus 8y. 24 plus 8 is 30. 24 plus 8 is 32 plus 16 is 48. So this is the tangent plane to the surface. And it also gives, just the way in Calc 1, the tangent line approximates a function at a point. In vector calculus, the tangent plane approximates a function of two variables at a point. So let me just do some problems to try and make this a little bit more concrete. So at the end of this section, this is section 15.6, exercise 13. We have a function of three variables. The function is x squared plus y plus z. Or we have this surface of x squared plus y plus z equals 3. And or it's like looking at the function capital F of x, y, z is x squared plus y plus z minus 3 equals 0. We want to find this level surface. And you'll notice that f of 1, 1, 1 is 1 squared plus 1 minus 3 is 0. And f of 2, 0 minus 1 is 2 squared plus 0 plus 1. Sorry, 2 squared plus 0 minus 1 minus 3 is 4 minus 4 is 0. So the points 1, 1, 1 and 2, 0 minus 1 lie on the surface. And we want to compute tangent planes at both points. Best recall the equation of the tangent plane, which is for a function of, for the level surface of a function of three variables. It is tangent plane equation. Partial of f with respect to x at ABC times x minus a plus partial of f with respect to y at ABC, y minus c, plus partial of f with respect to z at ABC, z minus c equals 0. So for this function, the partial of f with respect to x is 2x. Partial of f with respect to y is 1. And the partial of f with respect to z is 1. So if you let at ABC equal to the point 1, 1, 1, the equation of this tangent plane is 2 times 1 times x minus 1 plus 1 times y minus 1 plus 1 times z minus 1 equals 0, or 2x plus y plus z minus 4 equals 0 or equals 4. So this is the equation of the tangent plane at the point 1, 1, 1. What about the tangent plane at the second point, which is 2, 0, minus 1? So the partial of f with respect to x is 2x. So when x is 2, 2x is 4 times x minus 2. Partial of f with respect to y is 1. So plus 1 times y minus 0. Partial of f with respect to z is 1 times z minus 1 equals 0. That's 4x plus y plus z minus 8 plus 1 minus 7 equals, so this is, put this on the other side, 4x plus y plus 7 equals 0, right? Is the equation of the plane. Let's do another example. So let's say we pick example 17, exercise 17. So we have a function z is a function of two variables. Z is a function of x and y. It's the function 4 minus 2x squared minus y squared. And if we look at the points f of, let's see, f of 2, 2, you get 4 minus 8 minus 4 is minus 8. And f at the point minus 1 is 4 minus 2 minus 1 is 1. So the points 2, 2 minus 8 and minus 1 minus 1, 1 lie on the surface. So this is some surface in three-dimensional space, and both of these points lie on the surface. We want to calculate the tangent planes. So for a function z equal f of x, y, the equation of the tangent plane at a point on the surface is z equals the partial of f with respect to y at the point AB times x minus a plus the partial of f with respect to y at AB times y minus b plus f at the point AB. So, and what is the partial of f with respect to x for this function? Partial of f with respect to x is minus 4x at AB, which is minus 4a times x minus a. Partial of f with respect to y is minus 2y, so when y is equal to b, minus 2b, y minus b, plus f of AB. So at the point a equals b equals 2, and f of 2, 2 is equal to minus 8, what is the tangent plane? Z equals minus 4 times 2 minus 8 x minus 2 minus 2b minus 4 y minus 2 plus f of AB, which is minus 8. So this is minus 8x minus 4y plus 16 plus 8 minus 8 plus 16. Or if you like, 8x plus 4y plus z equals 16. And if you plug in 2, 2, and minus 8, it works. Now, you can either write it like this or z equals, just leave it like this, minus 8x minus 4y plus 16. They're equivalent. So that's at the point 2, 2 minus 8. And what about at the point minus 1, 1? So you have a equals minus 1 and b equals minus 1, and f of minus 1 is equal to 1. So the tangent plane is z equals minus 4a, minus 4 times minus 1 is 4, x minus minus 1 or x plus 1, minus 2b, b is minus 1, minus 2 times that is, sorry, the partial of f with respect to y, so minus 2b. So if b is minus 1, that's plus 2, y minus minus 1, y plus 1, plus f of ab plus 1. So this is 4x plus 2y, 4 and 2 and 1 plus 7. So that's the tangent plane in the second case. Now again, as I had mentioned earlier, in Calc 1, if you have y equals f of x, if you have a curve, this is the graph. Here is some point, so this is the point A, comma, f of a. And at this point on the curve, you have the tangent line. And the equation of the tangent line is y equals f prime of a, x minus a, plus f of a. And this is a linear approximation to f of x near a. That is, you have this curve and you have the tangent line, and the tangent line is really very close to the curve near this point a, f of a. So this tangent line approximates the function near a. And exactly the same thing happens when we have a surface in space. So here we have a point a, b, f of a, b on the surface. This is the graph. Here we had y equals f of x. Here we had z as a function of x and y. And on this surface, you have a tangent plane. And the equation of the tangent plane is z equals partial of f with respect to x at ab, x minus ab, plus partial of f with respect to y at ab, y minus a, plus f at ab. That's the equation of the tangent plane. And this is an approximation to the value of the function f at any point xy close to ab. So the tangent plane of z equal f of xy at a point AB is a linear approximation to f of xy. So let's look at an example of that. Suppose we have the function f of xy equals 5 over 1 squared plus over x squared plus y squared. So f at the point minus 1, 2 is 5 over minus 1 squared plus 2 squared is 5 over 1 plus 4 is 5 over 5 is 1. So f of xy is equal to 1. What is the tangent plane for this function at the point minus 1, 2, 1? So for this function, the partial derivative of f with respect to x is 5 over, when you differentiate this, you get x squared plus y squared to the minus 1 is minus 1 over x squared plus y squared squared times the derivative of this with respect to x, which is 2x. So f sub x at the point minus 1, 2, this is minus 10 times x. That's 10. X squared plus y squared. X squared is 1, y squared is 4. This is 5. 5 squared is 25. The partial derivative of f with respect to x is 2/5. The partial derivative of f with respect to y, differentiate with respect to y, you get minus 10y over x squared plus y squared squared. So the partial derivative of f with respect to y at the point 2, when at minus 1, 2, is minus 20 over x squared plus y squared. That's 5 over 25. It's minus 4/5. So the tangent plane has the equation 2/5 x minus minus 1 minus 4/5 y minus 2 plus f of xy. What is f of xy? 1 equals z. So z is 2/5 x minus 4/5 y. This is plus 2/5 plus 8/5 is 10/5, which is 2, plus 1 is 3. So the tangent plane to this function is 2/5 x minus 4/5 y plus 3, and this is approximately equal to 5 over x squared plus y squared near the point minus 1, 2. Right? When x is minus 1 and y is 2, this is 1. When x is minus 1 and y is 2, what is this? Supposed to be equal. This is minus 1. This is minus 2/5, minus 8/5, minus 2 plus 3 is 1. Right, that's exactly right. So this plane, this is the tangent plane on the surface at the point minus 1, 2, 1. And this is a linear approximation to the function near the point. Let me just do a calculation. Suppose I take a point close to minus 1, 2. So suppose I take f of minus 1.1, 2.1. What is that equal to? That's 5 over minus 1.1 squared plus 2.1 squared. What is that equal to? Let me just use my computer to figure that out. That's 5 divided by, let's see, 5 divided by 1.1 squared plus 2.1 squared So my computer says this is 0.8896 roughly. And what does this say? So this is the actual value at the point minus 1.1, 2.1. And when I compute this number at that point, I get 2/5 times minus 1.1 minus 4/5 times 2 plus 1. I get minus 4.4. No. 0.4 times minus 1.1 minus 0.8 times 2 plus 3. No, plus 1. That's right. My God. Huh. Wasn't so good. I'm surprised. I have 2/5 x minus 4/5 y plus 3. And that's supposed to be an approximation near minus 1.1, 2.1. So if I put in minus 1.1 and 2.1, it's not as good. I got minus 1.12. So something is way off here. What was my function? The function is 5 over x squared plus y squared. Well, I'm going to try and figure that out numerically. So, but in any case, so this is the lesson for today. Section 15.6. And it is, and this is really very important, because this it certainly will be an exam question. Given a function a function of 2 or 3 variables, it defines a surface, and you want to find, and for every point on that surface, there's a tangent plane, and find the equation of the tangent plane. That is what we need to do. Okay. And then next week, wow, we go on to the next section, 15.7, on maximum and minimum problems. And we'll do that next week. The following week, there'll be a review session, I think, on Monday. And there may be an exam coming up in about 2 weeks, but I'll have to double check our schedule about that. We'll see. But let me just make a note so you recall. This is still exam 2 will likely be on Wednesday, April 10th, on campus. So you might want to make a note of that. Okay, all. That's it for the day. I remind you, if you have questions, you should take advantage of the problem sessions. And if you can't make one of the scheduled problem sessions, email me and we'll work out a time when I can be available for you on Zoom. Enjoy the weekend all, and see you next Monday. Bye all.